Hi, my name's Abe, and in this video we're just going to give you a quick refresher on limits, as well as quickly introduce continuity and differentiability in really simple terms. Alright, so very quickly, just onto limits. So, remember, right, in our earlier videos, when we write limit as x runs to 0 of f of x equals, say, 2, what this means is this: that f of x gets infinitely close to 2 if x gets infinitely close to 0. So basically, what we're saying is that this limit idea can be applied for functions where, for instance, f of x may not be defined at 2, or something weird's going on at 2, but for everything else it's behaving perfectly fine. So anyway, the key here is that this is defined from both sides, left and right. So if we were to draw a graph, right, and let's say this is our graph, and this is the point A, and you can see that as I approach from the left, the y value gets closer and closer to f of a, if this is the line f of x. And also, if I approach from the right, the value of f of a also gets closer and closer to f of a. So the y value gets closer and closer to f of a. Right? So it's a both-sided limit. But what happens if the limit is different on both sides? So I can think of one example where this is true. For instance, let's say if f of x equals 1 on x. So you know what that looks like. Looks like that. Now what happens at x equals 0? Now you know that f of 0 is undefined. But depending on which direction you approach 0, your value that you sort of end up with is different, right? If you come along here, like that way, then you see that as you get closer and closer to 0 from the right, your y value gets higher and higher and higher, it eventually hits infinity. But if you come from the left, your y value gets lower and lower and lower and eventually hits negative infinity. So I'm just going to quickly introduce this idea that the limit as x runs to 0 from the positive side, so from the right, of f of x is infinity. And also the limit as x runs to 0 negative, so from the left of 1 on x is negative infinity. Simple idea, isn't it? So basically now you've got a way of distinguishing left and right limits. So this is from the right, and this is from the left. There you go. So yeah, that's how you'd express the limits in terms of this place, where the two limits, as they converge from both sides, do not converge on the same number. Okay, cool. So onto continuity and differentiability. Two long words that have kind of official definitions, but let's try not to talk about them. and we'll just talk about common sense ways of talking about differentiability and continuity. Okay, so the first thing I want to do is draw you 3 graphs. The first graph looks like this. It's a hybrid function. It kind of does that. Okay, so you see that at our point A, we have a bit of a discontinuity. There's a bit of a jump going on here, right? It's a jump here. Okay, the second graph I want to draw for you looks like this. Again, I'm going to call this the point A. This second graph, what's going on here? Well, it's joined together, but there's a bit of a kink right here, isn't there? It's pretty obvious where it was joined. Now, the third graph I'm going to draw, it's going to look like this. More subtle. But the point A happens here. The point A is where the straight line just begins to turn. Okay, I'm going to use this to demonstrate continuity and differentiability. Okay, so continuity basically says, can you draw it without lifting your pen or doing dodgy stuff? So this is a pretty simple concept, right? So the first one, the first graph here, the first graph, obviously not, right? There's no magical way of drawing the whole graph without lifting your pen at some point. So that's pretty easy. That's not very continuous. The second graph, you can draw without lifting your pen, can't you? It's just one motion. So this one is continuous. Now for differentiable, sorry, I'm not done yet. The third graph you can also draw in one motion, continuous, right? So I think continuity is the easier one. If you can draw in one line, continuous. Very good. What about this? Differentiability. And by the way, when we talk about continuity and differentiability, it's always at a point. At a point on the function, is this point continuous? Is this point differentiable? So here obviously we're referring to the point A. And so onto differentiability. Differentiability says this: at this point A is the derivative defined. So the first thing to note is that differentiability actually requires continuity. Oops, sorry. No, that's not what I want to do. Point. Okay. Differentiability requires continuity. If you don't even have a point, if you don't even have, like, you know, a straight a line defined, if your point is not even part of a line, then how can you hope to have a derivative at that point? It's not going to work, right? So first thing you need is a point, a line that's continuous. The second thing you need, it turns out, the second thing is that you need to be able to draw a clear tangent at that point. So do you see what's going on here? So we've already decided the first graph is not differentiable because you need continuity in order to be differentiable. What about the second graph? Looking at the second graph, you see that at the point A, which is this point here where I'm interested, this point here, I can draw a tangent like this, or like that, or like that. They're all kind of okay looking tangents. There's no single tangent that's correct. And that's because there's a kink in the graph, right? So the second one is, the second graph here happens to not be differentiable. But what about the third graph? The third graph, you see that at the point A, here, there is exactly one tangent I can draw, which is kind of like just flat, really. Kind of like that. And that's it. There's no other tangent that'll fit. Thus, the third graph is also differentiable. Yeah? So to summarize, differentiability is really determined by whether there's a kink at your point, like in the second graph, or whether it's just sort of like a smooth join, like the third graph. So basically the question is there a smooth join here? So yeah, two simple questions to ask when you look at continuity and differentiability. So if you're given a graph, you should be able to tell immediately whether it's continuous or whether it's differentiable. And remember that to be differentiable, you definitely need to be continuous first. Alright, well, I hope you've enjoyed yourself. I'll see you next time.